So, good morning. Happy Republic Day to all. This lecture, we are going to consider matrix representations of linear transformations on finite dimensional vector spaces. And we have already seen that matrices do give a wealth of examples for linear transformations. With all the intricate properties of matrices, it gives a wealth of examples. But the relation between linear transformations and matrices go far beyond this. In fact, matrices turn out to be representations of linear transformations. Now, this is the problem that we are going to look at in this lecture. Okay. So, what do we know already? We already know that if V is a vector space of dimension n over F, then V is isomorphic to a copy of F. Now this we have proved already, discussed already. You have also possibly looked at some examples. Nevertheless, it is worth recalling at this juncture. The reason is that it takes off, all these ideas take off from this point. So let us look at the following. So V is the vector space and this is a copy of it, right? Now if you take a vector V here, we are going to establish an isomorphism to F. How do we define an isomorphism? This is done as follows. Let BV an ordered basis we use the word ordered because the order in which V1, V2, etc., Vn appear is very important in our representation. For instance, we do not consider V1, V2, Vn and a non-trivial permutation of this, the indices, say V pi 1, V pi 2, etc., V pi n, where pi is some non-trivial permutation of the symbols 1 to n as equal. Because apart from the set theoretic equality, that is, you have V1, V2, etc., Vn on one side, and the other one is V pi 1 where pi is a permutation of the symbols 1 to n, a non-trivial permutation, and this is not equal unless pi is the identity permutation. This is what we mean by, that means the sequence in which V1, V2, etc., Vn appear is important. That's why we have used the word order. It's not merely the set theoretic equivalence of the set. For instance, these two sets are the same, but their order in which they are also placed is very important. Now you know that once we fix the basis, V has a unique representation. So let it is a unique linear combination of V1, V2, etc. Vn. What we defined, you recall, was the following. We defined a function phi from V to Fn by phi of V equal to x1 . This was the definition of phi, where V is given by x1 V1 plus x2 V2 plus xn Vn. Now you see that this is well defined because x1, x2, etc. xn are uniquely fixed, and the reason for that is BV is a ordered basis, and therefore the order in which these x1s appear is also unique. So let us denote by x, which belongs to Fn, and we have phi of V. Then phi is 1 to 1, on to, and so it's a structural isomorphism between V and Fn. This is something which we have proved. Now the important point is this: if B prime V is another order basis, V, then the corresponding isomorphism maps V to another entity. That is, if V1 prime and where y1, y2, etc. yn are uniquely fixed, then the corresponding isomorphism is psi of V equal to, which is uniquely defined, change of basis defines a new isomorphism. And we already know that for a vector space over F, the choice of the basis is not unique. And the choice of every basis fixes a new isomorphism. Therefore, there are several isomorphisms, as many as the basis, the ordered basis that you can choose, available from V to Fn. So what one has is this: there is another copy of Fn created isomorphic to V through the map phi. So what we can, the same element getting mapped to Y. So there are phi and psi are two different mappings. Phi is an isomorphism, psi is an isomorphism. Phi is different from psi in general, as long as the two bases are, two ordered bases are different. Okay, right? So this is the, so we have the luxury of creating several copies of Fn isomorphic to V through this process. This is exactly the the position that we want to take advantage of. So we keep this in our mind. Now I'll just give a example to drive home the ideas. Let us take V to be equal to all polynomials of degree less than or equal to 2 over F, including the zero polynomials. You know that is the usual addition of polynomials and scalar multiplication. It forms a vector space and is easily seen that a typical mapper of this is this. PIs belong to with the usual addition and scalar multiplication, this is a vector space. And you know that it's a vector space of dimension 3. And a basis, let us choose a basis BV that we choose as 1x square. You know that this is linearly independent as well as this spans the whole of V. Therefore, it's an ordered basis. Having chosen this, now one quickly observes that phi of P because what you have is this, that so we are, and you observe that phi of 1 equal to phi of x equal to essentially what you are doing is you are mapping the elements of the ordered basis to the ordered basis E1, E2, etc. En. That is the standard basis for Fn. Map it in this way. Okay, so that's about BV. But if you consider the same vector space, then we can choose another order basis. So let B prime be, I think I better look at this because the computations are involved. 1 plus t, 1 minus t. Now one checks easily that this is an ordered basis. We now let us compute this. So we take Px, which is equal to x square. Now this can be written as q naught into that means the first element, this corresponds to x1 v1 prime plus x2 v2 prime, or y1 v1 prime plus y2 v2 prime plus y3 v3 prime. That's what we have. Exactly this part that is being worked out. Now we have to, what is given is, what we know is P0, P1, P2, we do not know Q0, Q1, Q2. Now comparing the coefficients of the like powers of x, one observes that we have three equations to determine P0, P1, P2. They are Q0 plus, to determine I mean Q0, Q1, Q2. Three equations are there. Q0, then Q0 minus Q1 equal to P1. Then you have Q2 equal to P. So P0, P1, P2 are given and Q0, Q1, Q2 are to be determined. Now solving these equations, one gets the following. It's simple to solve. It can be solved because this is a linearly independent set and the original one that we have looked at is 1x, x square is also a linearly independent set. So we have the three equations to determine this, and from this you observe that the solutions are Q2 equal to P2, Q1 equal to half of P0 minus Q2, Q0 equal to half of P0 plus P1 minus P2. Just like that. minus 2n. We have minus p1 plus p1. Right. Therefore, the psi map is, this is equal to, the triple that you have is half of and P2. So this is the psi map that you have. Okay. Therefore, the vector P is identified with this two half of P2. Whereas the same element is identified with so the two different maps lead to different representations. So you see that this is what I said, that there are several representations possible. So that is in fact some handicap. Which one to choose will be a problem that we are going to face. But we are going to turn that around to a great advantage. For example, if you just work with this one, you see that phi of a specific case 1 plus p square is equal to minus 1, whereas psi of this is equal to 3 by 2, 1 by 2, so phi of so that is what we observe. So there are various representations possible in Fi for the same vector based on what particular ordered basis that you choose. This is an important point. Now let us take this discussion further and we start looking at what are called linear transformations. So we enter the main area of the subject, the topic of discussion today, the representations of linear transformations. So that gives a flavor of things to come. Now let V be an n-dimensional vector space over let T belong to LVW. LVW stands for all linear transformations from V to W. Let us choose ordered basis for both V and W. Fix that and then proceed. So we take VV this has n elements and this has m elements. They are linearly independent. They span the respective spaces. So this is an ordered basis. V now you know that a linear transformation is completely defined if you prescribe its image, the image of a basis under that linear transformation. For example, all that we need is we have already chosen a basis here. Therefore, let us do that and then we will get it. So we prescribe the following: define, or rather than defining, let TVJ be equal to sigma I equal to 1 to m A W. What does this mean? You see that this is V, this is W. Now what we have is V is here, an element, T is the linear transformation, and this is your TV. Now TV is an element of W, and therefore it has a unique representation in terms of the ordered basis for W. In particular, for each J, if you take TVJ, it's a linear combination of W1, W2, etc., Wn. And the coefficients that appear here are from the field, associated field. They are uniquely defined. They are uniquely determined because V is n-dimensional, W is m-dimensional. Then VV and VW are basis for V and W respectively. Alright. Now this is defined for all J's coming from J belong to J. Okay. Suppose you can take Vj here. This is mapped by P to sigma I equals to n. That's the mapping that you have. So let us mark this. Put it inside the box. You should be careful here because you want to get ultimately the matrices as Aij. So we are keeping this J fixed, that is the second index fixed, and the first index is over which you have the summation. So in Aij, when we define Tvj, we are writing it as not as Tvi equal to Aij Wj, not that way. We are writing it as Tvj equal to sigma Aij Wi. Okay, so that is for certain convenience which you are going to see why, how it is going to help you. So you see that A1j Mj are the coordinates of Tvj in terms of so this is a vector in Fn. Okay, this is a vector in Fn. So we are going to work on that. Now see the picture that emerges is this. Okay. So you have V W. Now you have got an isomorphism. Once we choose BV, then there is an isomorphism phi defined. Defined from V to phi. So this is one representation for V. Now it's an isomorphic image of V under phi. So phi is well defined. Now what you have is V is mapped by T to W. T. Okay. Now what do you have? You have a ordered basis BW here. W1, which we have already chosen. Now in terms of that, now you see what you have is here. This is written as x1, e1. It's the unique representation of P. And that prompts us to associate this with the element x given by, here the order is very important. Now what do you have? TV. TV is an element of W. So TV turns out to be something like y1 w1 plus etc ym, that's again a unique representation of TV in terms of the basis W1, W2, etc., Wn. So now what you do? You have a copy of it. Yeah? So now you see that there is a isomorphism psi of W to Fm, and you see that TV is mapped onto Y1 which we designate as okay. So what you have? You have an X here corresponding to V. You have corresponding to TV. You have a Y here. Now what we do is we define a map from Fn to Fm. Okay. We designate it by A or sometimes T. We just designate it by A. Now what is the image that you have? For X, the image is, so this is called AX. Okay, AX is equal to Y1, Y2, etc., Ym. So you have AX define, this is the definition of A, where A is fixed by these numbers that come. So what are they? So you have here Y Yj equal to Yi equal to sigma no, I think we look at that. So this is the connection that we have. Okay, let us get it up. So I have not proved this, I am just going to show this. Okay, what do we have? So let us work out. It's easy to make the computations. We will leave the diagrams over here as they are. Okay. So what you have is that let now TV is then equal to x1 TV. That is because of the linearity. and this is equal to summation over j xj sigma I equal to 1 to m aij wi. Therefore, what do you have? Now, you see, these are all finite sums. J running from 1 to n. So, these are all finite sums, and you are working with elements of a field. Therefore, you can easily interchange them. It does not change the sum at all. Okay. Therefore, I interchange the sum. And I get sigma I running from 1 to m sig of one to n aij xj w. So what does this show? This shows that the coordinates of TV given by y1 ym according to the map side is, so this I write as sigma I equal to 1 to m, this is actually yi w. Sigma what is that you have? You have j running from 1 to n and I is 1. So sigma a1j xj sigma a2j xj a sigma amj. This by this identification, that is, so what we are identifying is that yi equal to sigma aij xt, j running from 1 to n. This is the identification that we have made. That's exactly what we have here. Okay. Okay. So what have you obtained? Started with MD, its image is X. Map it with T, you get TV. TV is now given a representation in terms of the ordered basis BW, which gives you the coordinates y1, y2, etc., ym of TV. Now you are defining A as mapping the vector x1, x2, etc., xn to y1, y2, etc., y. Okay. Now let me take over this. So we write now the vectors x1, x2, etc., xn as a column vector. Okay. So identify This is in Fn. This is in Fn row. Similarly, you identify with the column vector this is an element of F and cross F. Now we have yi equal to summation over j aij xj, j running from 1 to n. Therefore, we just write it up in terms of our matrix multiplication. Suppose you have, see, so what you have is this x1, this is an observation. Multiply by the m by n matrix a11, a12, a1n, a21, These numbers we have determined in this way by looking at the images. Already we know how we have obtained those numbers. This is what you have. This gives you your y1, yn. And that is essentially, if I write it in detail, this is sigma a1j xj, sigma a2j xj, sigma a mj xj, 1 to n, 1 to n, 1 to n, j running from 1 to n. This is just the standard matrix multiplication. Therefore, we have now, we write it has to be careful about the indices that we use to get it right. So ax, x taken as a column vector is equal to y, where A is the aij for as an m by n matrix belonging to it's an element of m by n matrices over F. Now 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to k. Okay. So what do we have? We have now defined A maps x to ax. So for every v getting mapped to TV here, there is a corresponding action taking place from Fn to Fn. Okay. Now this is denoted by A, and if we use the column representation or identify this with the F n cross 1 and this with F m cross 1, then you see that this is merely your matrix multiplication that you are talking about. Okay, so this is a map. Now the questions that you ask are, okay, now all m by n matrices represent linear transformations from Fn cross 1 to Fm cross 1. Therefore, this is a linear transformation. Now A is and the linearity, to prove this linearity, what you do is you have, see, you have the notion like, okay, let us prove this. Then we can write this. Come to that. Now we shall prove that this is indeed a correspondence that works here. Okay, what is that you have to do? Take two vectors here. Look at the corresponding maps PU and the images of those two vectors. Sum of these vectors will get mapped to the sum of the images. That is clear because P is linear. Now you set up the corresponding representations in Fn and the corresponding representations of the images in Fn. Check whether the sum of these two is identified with the sum of these two. Similarly for scalar multiplication. So you have to check that. Okay, so that we will complete that. Now, so we have the following theorem. That is routine. Okay? The very fact that this is a linear transformation, a matrix represents a linear transformation, proves it. Okay? So you have to prove the following, that is, if now let x and x to the images of and let x and x tilde respectively y and y tilde with respect to this is BW. Then the picture that emerges is this: T is linear, T of CV plus V tilde. V plus V tilde is represented by, is identified with C x plus x tilde. T of CV plus V tilde being linear, this is equal to C TV plus TB tilde is identified with CY plus Y tilde. Okay. Now what you have? What you have is that AX equal to Y and AX tilde equal to Y tilde. This is the representation. Therefore, you have see TCV plus V tilde is represented by what? So you have X plus is mapped to what? X tilde. And this you know is essentially C of AX plus, where A is by derivatives AX. Therefore, A is a linear transformation. So what you have is that A is a linear transformation from or slightly distorting the whole thing. This can be considered as from Fm to F. So this is the representation. So we start with a linear transformation. There is a corresponding linear transformation from Fn to Fm or Fn cross 1 to Fm cross 1. This is the picture. Okay, so we will write down that here. Let V and B, N and M dimensional vector spaces over let B be an ordered basis for V and dW W. Let T belong to L W. Then where exists and M5 matrix A with entries F such that the representation of dV with respect to is equal to A times the representation of V, where these correspond to the column vectors. The notation is that M and Xn and A This is the further the association P corresponding to A, so is a 1-to-1 isomorphism between N 2. Okay. So how do we go back? Now, this also has to be. This is the picture that you have. Okay. Now what you say is that, see, T belongs to LBW. It's a typical member of that. Correspondingly here, you have the all M by N matrices. So let me denote this by M Aij. Okay. A is now what you have is that given A, okay, there is a corresponding T. How does that come? Comes like this. See, given A maps X to AX. Go backward through phi. You get a particular B here. Okay. So phi inverse of X is equal to B. Then phi sine inverse of AX is an element here. Now write T of B equal to the image element W here. That gives you a transformation T and it is linear. Okay. So you have got corresponding to each T fixes an A. If you take an A here, it fixes a particular C. Okay. So what we do? We just note down these things that what is A? A is in fact, is what you have, phi inverse of phi inverse T and then psi. Okay, you know that both phi and psi are isomorphisms, right? By obtaining the following, that Ax equal to psi T phi inverse of X, which is equal to phi inverse of X is B. So this is equal to psi of T. Okay. Which is equal to Y, and we have A, which is equal to Ax. This is what. Okay. So you get this relation. Similarly, so A belongs to Similarly, what about T? By work like this. Okay. Take phi here, then A, then phi inverse. This operating over x. Sorry, operating over Fn. This is your Fn. Which can be identified with Fn and Fn. Once A is given, you have a T determined. Then T is. See, all these are isomorphisms. Both phi and psi are isomorphisms. Play a very important role. Both. So this is the identification. A is identified with a linear transformation. T gives A gives. So for any linear transformation, so any element of M cross N, F, there is a corresponding linear transformation and vice versa. That's why there is an isomorphism. So this is the isomorphism for that we therefore say that this is the identification. T, the matrix representation now with respect to BV, PW equal to 0. This is the identification. Okay? And this is an isomorphism. Now, one of the important remarks that I want to make at this stage is that certain remarks I want to make at this stage, they are this. A represents T relative to the ordered basis so in general, therefore what happens? If you change the basis, the representation also will differ. Okay? So a change of basis In other words, the same linear transformation P belonging to different representation even a change in the order of the basis will incorporate a corresponding case. Even a change in the order that's important. Okay. So if there is no unique matrix representing a linear transformation except in the case of identity and zero. Okay. Except for the zero linear transformation. And this is represented by the zero matrix. For any choice of the ordered basis in all other cases you get a different matrix. Even an interchange of the order or a change brought in the choice of the basis, ordered basis, makes a change. Now I think I will continue with the remarks in my next talk, and then we also have a look at some of the examples which will give some insight into what goes on. Okay? So, thank you very much.